So it's a pleasure for me to introduce today's speaker. He is Professor James Arthur from the University of Toronto, best known for the Arthur-Silver trace formula. And he's a well-known Canadian mathematician. He has received a number of awards, including the Hertzberg Medal and the Theorem Field Prize. And in order to introduce him, we will talk about the classification of representations.
So don't forget to turn this.
He's backstage.
Thank you, Alejandro. This being the last plenary talk, I maybe should just thank the staff for the wonderful job they have done organizing this Congress. And I will just add that I have a personal debt to Yuriri, I believe her full name is, who at the last minute, 2 days ago, when I found that my clumsy handwritten slides were completely inadequate to the size of this room, teched it all very expertly and finished it 25 minutes ago. So I'm very grateful to her. Thanks. So the contents, in principle, the contents of the talk are in a volume published by the AMS, which will be in print in a month or two. I say in principle because I will spend probably most of it, even the whole talk, trying to set the context for these results in the general area of automorphic forms. This being a plenary talk and automorphic forms being really a notoriously technical subject, it's not easy to give an idea of the subject in such a talk. I will do my best, but I think it's best not to present too many very precise definitions because they often will pile up and people will get lost. So I prefer to argue by how people in the area think of these things, or at least how I think of them, with perhaps even analogies and metaphors, which to me are very helpful. Okay, so automorphic forms, that's the subject. I don't know if you saw the excellent presentation of Fermat's last theorem on nova, but the person that was doing it amused himself by asking quite a number of prominent mathematicians to define an automorphic form. And they must have been caught unawares, and he switched from one to the other, and none of them really gave a very adequate definition. But I think, without giving a precise definition, automorphic forms, the reason they're interesting is that they are eigenforms, or if you prefer, depending on how you present them, eigenfunctions of actually a whole lot of simultaneously commuting operators, and therefore coming with a whole lot of different eigenvalues, which are of great arithmetic significance. So more precisely, the way I've set it up here, they're eigenforms of natural operators that really seem to be everybody treats as kind of objects that occur in nature, Hecke operators, as they're called, on certain Riemannian manifolds, which are called specifically arithmetic symmetric spaces. So now here's an example of such a thing. This may be a little not familiar to everyone, but I just present it now because it is the canonical, I would say, the canonical manifold in which these things arise. It's perhaps the most famous one in a higher rank. It's known as the Siegel upper half plane. It is a double coset space here we have the symplectic group, the group of symmetries of a 2n by 2n, the standard, in fact, 2n by 2n symplectic bilinear form. That's what that is. K is, so you take the real points of that, the set of real matrices, symplectic matrices that stabilize, that are symmetries of this form. And then you take K, well, it happens to be the unitary group on n letters, but it's a compact group, and in fact it embeds in this symplectic group in a natural way, and is a maximal compact subgroup. So that's what you're doing up there. You're modding out by K on the right. On the left, however, to make it more interesting, you're dividing out by a discrete group, the group of symplectic matrices with integral coefficients, which are congruent 1 to the identity matrix modulo some predetermined natural number. So Xn can be shown, it's well known. It's the set of complex points of an algebraic variety, but it comes with operators. It's not just a complex algebraic variety, but it comes with a whole family of operators on, say, its cohomology, or if you prefer, just its set of functions that come by doing left translation, that's over there, by GQ, the rational symplectic matrices. So you might say, well, you can't do that because you're not going to stabilize gamma sub n. And that's quite correct. The normalizer of gamma n is not contained in there, but it does stabilize gamma of n. It does conjugate gamma of n to a different subgroup, but whose intersection with gamma n is a finite index. And so what you do is, because you're dealing with functions here, or form, or cohomology here, you can simply average that over a finite subgroup to get another form that's invariant by this. So this comes with a huge family of very natural operators. As a matter of fact, if you restrict yourself to rational matrices whose entries have denominators that are relatively prime to n, the resulting collection of operators is commutative. It's an algebra of operators which is commutative, and in fact it basically is a direct product of of algebras, very sort of natural algebras, over all the prime numbers which are relatively prime to n. So what have you got? You've got something that's really very interesting. You have a natural, God-given space with a whole collection of very interesting mutually commuting operators, which can therefore be on a space on which they can therefore be simultaneously diagonalized. So it comes with a whole family of really concrete information, data, the simultaneous eigenvalues of these operators. And as the operators vary over the prime numbers, the eigenvalues of these things are believed to carry information that is absolutely fundamental in the study of the arithmetic world. So this space may be a little unfamiliar to many people. You might, however, be familiar with the case if you take n equals 1, because SP2 is the same as SL2. So you'd be talking about SL2R modulo what is basically SO2, and that's the upper half plane.
Is that supposed to be UN rather than SUN?
Yes, it is. Yes, thank you. It is supposed to be UN. Thank you. How do I get rid of the S? I can't do that. It's like, thank you. It's UN, and so when n equals 1, it is SO2. In that case, you have the upper half plane, and you're dividing out by a subgroup of the modular group, a very familiar and well-studied and extremely important object. So this is a higher dimensional analog of that. Okay, so now this is one of the deepest notions in the subject, the notion of a motive, which was discovered by Alexander Grothendieck, I guess in the 1960s. These are fundamental, I should say, to be honest. The definition that Grothendieck gave of a motive is still based on fundamental standard conjectures which have not been resolved. So the definition of a motive, the precise definition of a motive, is still not available. But everybody believes in their existence. They are fundamental as such. They're fundamental constituents of algebraic varieties. They are very deep. They're very abstract. They amount to, one way to think of them is they are sort of fragments of the cohomology of algebraic varieties. Now, I'm told that when Grothendieck discovered these objects, he made inquiries to friends of his who were artists or in the humanities, and motive is an English translation of motif in French, and which is a well-known notion in art, literature, and music. And it stands for sort of abstract fragments or ideas which somehow govern the larger body. I mean, I guess, for example, I guess Wagner in his later years used motifs, which I guess he called leitmotifs, increasingly, and they stood for characters, or they stood for objects, or they stood for ideas even, or even feelings of the characters, which were only subconscious for them, but which you, the audience, got to see. And I think it's a very apt analogy with the role they appear to play in algebraic geometry. Excuse me. Another analogy I think is fair is with fundamental physics. If algebraic varieties model the objects of everyday life, well, I don't really, as Manjul in his wonderful talk yesterday recalled that they really are model two-dimensional or even-dimensional objects, not three-dimensional objects. But leaving that aside, algebraic varieties, it's fair to say, they model sort of the everyday objects that one would see. If that's the case, then motives, I think, would model the fundamental particles that compose these objects. In fact, in our wildest dreams, or maybe I should say my wildest dreams, I don't want to blame this on anyone else, I might imagine that this is more than just a metaphor with physics. But in any case, the way motives work, it seems to be an apt metaphor. Okay. Well, the language, I've described an automorphic form in general terms for the example of the Siegel upper half space, geometric object, but actually the language of automorphic forms is really representation theory. It's equivalent, in fact it's more general than their description in terms of geometry, but it's more efficient. It brings in, for example, harmonic analysis in the following context. And again, this is a little bit technical will be for many people who are not familiar with this, but it's really the best way to phrase things. And so what you take G to be a reductive algebraic group over Q, and then you can take its Q rational points, and that then embeds as a discrete subgroup of a locally compact group consisting of the adelic points in the group. And then R, one would take R to be the regular representation of GA by right translation on the Hilbert space of square integrable functions on GA over GQ. If you're not familiar with this, perhaps think of Fourier series. It would be, well, it's not quite a special case of this because it's not reductive, but it would be mount to the special case of this where GA is the additive group of real numbers and GQ is replaced by the discrete subgroup of integers. And then you'd be looking at L2 of R over Z. And its decomposition into irreducible representations is the theory of Fourier series. Or you could take the discrete subgroup just to be the identity. You'd just be talking about L2 of R. And there, the decomposition of R is given by the theory of Fourier transforms. It decomposes continuously as opposed to Fourier series, which decompose discretely. The interesting thing about this is, The interesting thing about this is that there is, in general, a discrete part of the decomposition of R and a continuous part. So it encompasses, in a formal sense, both phenomena that come into Fourier series and Fourier transforms. So then an automorphic representation, that's up at the top there by definition. And this is a somewhat restricted definition that I'm not making precise, but automorphic representations are irreducible representations of GA, of GA, which occur in the decomposition of R. Should I turn off my microphone as I sip the water? I don't know whether. Okay, so it's a formal fact, which I will say in a little bit more detail in a few moments, that the data in Heck operators, these sort of really fundamental and interesting numbers, these eigenvalues of these operators, that actually that's wrapped up in the data that goes into an automorphic representation, an irreducible representation of GA that occurs in the decomposition of R. Okay, so Langlands was the person that really just formulated all of the basic results and conjectures in this area. There are two pillars, I would say, of the Langlands program. They're both conjectures. They are conjectures that are very far from known. They're magnificent conjectures. The first one is known as the Reciprocity Conjecture, of which I will simply give an informal version. And it is the data that characterize motives. So these are these hidden objects at the heart of algebraic geometry. The data in motives are contained in the data of automorphic representations. So these eigenvalues of Hecke operators are not just sort of interesting natural phenomena, but they go much further than that. They are believed, according to this conjecture, to include the data that characterize these hidden and mysterious objects, motives, which in turn are the constituents of algebraic varieties. Now, when I say algebraic varieties, I mean, actually, strictly speaking, I mean projective non-singular algebraic varieties defined over a number field. This conjecture says that whatever characterizes these things, you can find it in a very explicit way in automorphic representations. There's a very precise version of this conjecture, which I won't give. what is a remark that I wish to add to that? Well, I'll think of it in a minute. Very deep conjecture. Oh yeah, I guess there was a couple things I wanted to say. If I'm thinking of motives, if I'm thinking of them in terms of this metaphor with physics as fundamental particles that compose the objects of everyday life, then what does this conjecture say? Well, I would argue that it amounts to a classification of these fundamental particles, along with data that gives all of their properties. And if you're thinking in terms of particles, things like the mass and the spin and all of the other physical quantities that are thought to be in fundamental particles. These would be represented by the data in automorphic representations. Now, there's a very famous, this is very, very far from being proved, but a very famous case of it has been proved, and I mentioned at the beginning that the Siegel upper half space, if you take n to be equal to 1, it becomes the upper half plane modulo suitable discrete subgroup. Well, the elliptic curves that Manjul talked about yesterday are part of this conjecture, a very specific part of it, which is known as the Shimura-Tanyama-Vey conjecture, namely that elliptic curves, well, one way to say that is the motives, the sort of most interesting motives in elliptic curves, actually can be represented as a piece of the upper half plane. Well, that's not quite correct. One has to take the cohomology of the upper half plane modulo a discrete subgroup, and then I guess one has to take a Jacobian of the resulting curve, and then look for an elliptic, for a one-dimensional factor of that. And this is still not completely correct, but the conjecture says that any elliptic curve defined by Manjul yesterday can be represented as something that you get out of the upper half plane modulo a discrete subgroup, an arithmetic congruent subgroup, in fact. Of course, this was the proof by Wiles was a fundamental, revolutionary advance. And as we all know, it was known that if you could prove that, you would have Fermat's last theorem. And Wiles proved most of it, and certainly enough of it to establish Fermat's last theorem. So that's a very special case, the case n equals 1, in fact, even a very special case of n equals 1, of this reciprocity conjecture, which tells you that similar things, which asserts that similar things are true for arbitrary varieties. In particular, they would be true, according to this conjecture, but yet far from known, for the hyperelliptic curves. The hyperelliptic curves discussed by Manjul, which were the generalizations that he described of elliptic curves. So a really magnificent conjecture. It includes also the data that would characterize, since zero-dimensional motives are just solutions of an equation in one, or are obtained from a solution of an equation with rational coefficients in one variable. It would include data that would characterize or classify Galois extensions of the rational numbers. In short, it would include data, automorphic representations would include data that really characterize some of the most important objects in the arithmetic world. So that's the reciprocity conjecture. All right, so that says you got to look at automorphic representations if you want to find a classification of these arithmetic objects. The second is known as the principle of functoriality. Again, due to Langlands, it's called a principle, but it's a conjecture, a very big and difficult conjecture, closely related, as it happens, to the reciprocity conjecture. Very far from known, just as difficult, but it says there is a precise, you're not conjecturing that the law is precise. There's a very precise law, which I will actually describe in a moment, But there is a precise law which relates, okay, so if the data in automorphic representations is supposed to contain, or if that's the stuff we're supposed to be looking at, all right, we look at it, and this is a refinement of, it's the way you might want to look at that data. It says there's a very precise law which relates data of automorphic representations on different groups, G. Because remember, automorphic representations can be attached to any reductive group over the rational numbers. So I'll describe this reciprocity law in a moment. So to set it up, I'm going to make an assumption on G. I'm going to assume that G as a group over Q is split. Well, that's a group like GLN, the group of n by n matrices, and we'll keep that in mind in much of our discussion. And what was at the basis of Langland's conjectures on these, there were really many conjectures, but I've tried to summarize them as these two fundamental conjectures. But what was behind, largely behind many of Langland's conjectures, was attaching to any group G another group, G hat. It's actually a functor relative to a certain category. You restrict the morphisms, excuse me, of groups G, but in any case, it's a functor. From G to G hat being called the dual group, and it's a complex, it's a simpler object, it's a complex reductive group. And the dual group, if I'm arguing by analogy with Fourier transforms, then the irreducible representations of the additive group of reals are the exponentials, e to the x times lambda, x being the variable in the reals, and lambda, well, we could take it to be a complex number parameterizing an irreducible representation. So if we were thinking of that, then G hat would be the group of the additive group of lambdas, the complex group, the complex numbers, and they stand for basically the parameters that characterize irreducible representations. So, in fact, in Lie theory terms, if you're familiar with that, you have Dink and Coxeter diagrams that characterize simple Lie algebras over the complex numbers. And G hat, if G is given by a diagram, G hat is given, among other things, by the dual diagram, which a notion that makes sense in that context. All right, a little bit more technical here, but if you're not familiar with it, just maybe we'll look at the bottom line and work from there. The adelic group GA up here, whoops, wrong thing, I need to use the pointer. So the adelic group up there is what's known as a restricted direct product. It's a product of over all valuations on Q of their completions, QV. In other words, it's the direct product of GR, the real points, with the restricted direct product of the group over all of the p-adic numbers. P-adics being a completion of the rational numbers with respect, very much like in the spirit of Dedekind cuts that we all learn about as undergraduates, as a construction of the reals from the rational numbers. Well, the p-adic field is constructed in the same way. It's just you don't use the absolute value, but you use another kind of absolute value that's based on the divisibility properties by a prime p. In any case, the restricted direct product is not quite the direct product. It's a subgroup of the direct product where you take objects here, up there, which for almost all V lie in the maximal compact subgroup of GQV. And then you put a direct limit topology on that makes it locally compact. The problem is if you take a direct product of infinitely many locally compact spaces, it's generally not going to be locally compact. But if you take this restricted direct product, it will be. And then an irreducible representation is a corresponding restricted tensor product of irreducible representations of these groups, QV. Okay, so that's fine. But let's forget about that. A basic fact is, for almost all p, so pi here is an automorphic representation, as I've defined. For almost all p, pi p is unramified. Now, I'm not going to say that exactly what it is. I guess what it is that pi, to be unramified, pi has the property that if you restrict it as a representation of GQP, you restrict it to the maximal compact subgroup of that, which would be G with coefficients in the ring of p-adic integers, that it contains, that a restriction to that contains the trivial representation. And then it's known that it would contain the trivial representation at most once. So it's a fact that pi p is unramified in this sense for almost all p. And then there's then a classification, a very simple classification of unramified representations based on something known as the Satake transform, which asserts that there's a bijective correspondence between unramified representations and very simple concrete data. Semi-simple conjugacy classes, which I'll write as C pi p, in this complex dual group. So we can be thinking of the general linear group as our group. Then the dual group, it turns out, is in fact just the complex general linear group. And so you'd be thinking of semi-simple conjugacy classes in GLNC if you were dealing with the general linear group. They would parameterize unramified representations of GLN, QP. All right. Very nice consequence of this. What it says is that if you have an automorphic representation pi, and I'm going to write A, script A of G for the set of all automorphic representations, then it maps to something very concrete. It maps to something which I'll write as C pi, namely just the aggregation of all of these semi-simple conjugacy classes. You can't take all primes, you have to take almost all of them, P outside some finite set. And I'm going to write the set of such objects as script C of G. And I'm going to, I'm taking this map to be surjective, so I'm going to write script C of G to be the image of this. In other words, it's a set of families of semi-simple conjugacy classes in G hat. And in order not to have to make this set S play any particular role, this finite exceptional set, I'll take them up to the equivalence relation, saying that two such families are equivalent if they're equal for almost all P. So you could let that set be S be as large as you want, and you'd still get something that I'm going to be calling an object in C of G. So I'm going to take C of G, not the set of all such families, but rather the set of such families that come from automorphic representations. Well, this is very concrete data that we can associate to an automorphic representation. What's particularly interesting is not the individual numbers, a given C pi p, although that itself might be interesting, but what's really interesting is the implicit relations among these different families of numbers that are imposed on you by the condition that pi be automorphic. That's a very strong condition on an irreducible representation of GA. And what it translates to is very strong and interesting conditions on the relations between these different conjugacy classes in a given family, in the family that comes from a given pi. So I won't go into much detail about this, but these are the objects that give the eigenvalues of Hecke operators, these families of semi-simple conjugacy classes. It turns out that the Hecke operators can be represented as at a given P, the algebra of Hecke operators can be represented as a given convolution algebra on this space of double cosets. And this Satake transform that I mentioned actually represents this algebra as basically a polynomial algebra. This is for a given P as a polynomial algebra in the set of all such conjugacy classes there. So it gives a very clear and explicit representation of the eigenvalues of them. But I stress that what's really interesting is the relations among these different eigenvalues that are imposed upon you as p varies by the condition that pi be automorphic. Okay, so now I can give a precise version of the principle of functoriality. If you're given two groups, G and G prime, so these are now, we're taking them to be split groups over Q, and given a homomorphism. So now you've got their dual groups are two different complex groups. And suppose you have a homomorphism from one of these complex groups to the other. Those things are sort of basic staples. So such homomorphisms are basic staples of the theory of Lie groups. You can, at least if you're dealing with GLN, you can write them all down. It's Weil's classification of finite dimensional representations. Or let's say the second group is a general linear group. So G hat is GLNC, then you can write all of these things down. So the assertion is that, remember, this is not a theorem, this is a very, very deep conjecture. The conjecture is that given any such homomorphism, well, that's going to map conjugacy classes in G hat prime to conjugacy classes there. And the assertion is that it maps, it's then going to map this family attached to automorphic representations of G prime into the family of automorphic representations attached, the family attached to automorphic representations of G. What you would expect without this is that you're going to get a bunch of families of conjugacy classes for G, but they may not have anything to do with an automorphic representation of G. Automorphic representations are very hard to compare directly between different groups, but this says they bear this sort of fundamental relationship to each other. Or in other words, given an automorphic representation of G prime, there's going to be an automorphic representation pi of G such that the image of this family of semisimple conjugacy classes attached to pi prime is in fact the family of semisimple conjugacy classes attached to the automorphic representation pi of G. Very, very simple if you think about it. A very simple relationship between very concrete data. But what's remarkable is its depth. Maybe I just mentioned that if G prime is SL2 or GL2, and G itself is GLN, roughly speaking, there's one, if you were taking SL2, there's one representation for every dimension gotten by the action of SL2 or GL2 on the space of quadratic forms of dimension n minus 1. And so you're asking for that one n-dimensional representation of GL2, you're asking for a correspondence of automorphic representations. Even that apparently simple case is very far from known. If you knew it, it would imply a resolution of the famous conjecture of Ramanujan. Even Richard Taylor, in a remarkable paper, didn't prove that conjecture, but he found an approximation he proved a weaker version of it, and that was the core of his proof of the Sato-Tate conjecture on the distribution of Hecke eigenvalues for the group GL2. All right, so now let's get more concrete. These dual groups, I want to stress, are really pretty concrete objects. So I'm going to now assume that G is a classical group, and I'll pick a representative for each of the four families of infinite families of Dynkin-Coxeter diagrams. So the family of type AN, this is actually reductive, it's not simple, but that's okay. It's got a one-dimensional piece to it. And I'll take G to be GLN, where n is little n plus 1. And then, as I've said, G hat is GLNC. And then Bn, that's for that representative of that, I'll take an odd orthogonal group, SO2n plus 1. And in that case, you may, if you're familiar with this, you may know the Dynkin diagram of this. If you were to flip the arrows in it, you're going to get the Dynkin diagram of type Cn. In other words, G hat is equal to sp2nc. In the case of Cn, I will take G to be sp2n, and we can be working with that, thinking of the example I did at the very beginning. And then G hat is, again, the other way around, SO2n plus 1c. and find if G is of type Dn, G is SO2n, and G hat is SO2, it's just itself, like GLN, it's just SO2nC. Okay, so those are the various dual groups that you attach to these classical groups. All right, so let's look at GLN. What's a semi-simple conjugacy class in GLNC? Well, we know that it's diagonalizable, so it's just a set of it's just a diagonal matrix of non-zero complex numbers. And so an automorphic representation of GLN gives a family of such things parameterized by almost all prime numbers. So that's, of course, very concrete, just n different complex, non-zero complex numbers. It's supposed to be a conjugacy class, so we consider this to be an unordered tuple of n numbers. We don't mind permuting them. That's what conjugacy would mean in that context. Very concrete. And now we have a very remarkable theorem. I've actually joined two theorems, both of which were sort of very important, I would say. One by Jacquet and Schleike, and the other by Möglin and Waltzberger. And together, they make the following assertion. They say that if you map an automorphic, I'm going to write, for simplicity, I'll write A of n for the automorphic representations of GLN. All right, so you take an automorphic representation of GLN, and you map it to its family of conjugacy classes in the dual group. Again, I'm going to write that as C of n instead of C of GLN. But this mapping is injective. That's injective is the key part of that. By the way I've defined it, this is the image of the mapping, so it's injective and hence surjective. Injective, I mean, that's, what's that saying? It's saying that this very concrete set of data that you attach to an automorphic representation of GLN completely characterizes the representation. The data gives the representation. So all of the data that's in an automorphic representation comes or is wrapped up in this family, C sub. I forgot to write C sub pi there. I mean, pi goes to C sub pi, little c sub pi, in this collection there. So all of the data that's wrapped up in C sub pi completely characterizes pi. And so if we believe in the reciprocity conjecture, all the data in motives and sort of governs the arithmetic world is wrapped up in this, for GLN at least, in this little c sub pi, this very concrete family of eigenvalues. I just ask the question, well, it would be great if we could figure out what the image of this is. What are the set of all families for GLN that come from automorphic representations? What's the set of all automorphic families, C sub pi? Unfortunately, the question's too broad. You just, need another row there. The question is too broad. There's no simple answer. It would imply that you could write down all the eigenvalues, explicitly all the eigenvalues of the Laplace operator, say on the upper half plane modulo an a congruent subgroup. You can't do that. That would be a very special case of this. So it's much too broad. Whoops. So if we think of Langland's point of view, he would say, I guess, well, that question's too broad. You're not going to be able to answer that. I get too excited on this and push the wrong button. But his point of view would be functoriality. All right, you're not going to be able to characterize it, but there's nonetheless many deep and concrete relations among the sets C sub G attached to different G, or even for GLN. You know, one like GL2, as I mentioned, GL2 into GLN. There's the set for GLN includes sets attached to GL2. So even though you can't characterize the image, in explicit terms, there's many interesting relations as G varies among these sets. All right, so now so that's GLN. So GLN's really good. We know all kinds of things about GLN. We know how to define L functions for GLN, so-called Rankin-Selberg L functions. We know how to thanks to Jacquet and Schleike and Piatetsky-Shapiro, we know how to analytically continue them. We know with functional equation, we know about Whittaker models for GLN. We know many, many things about GLN. But these other groups, they're more problematical. So remember, what I'm going to be doing then is to take these other groups of type Bn, Cn, and Dn. But what I'm going to do, G hat is a matrix group in each case. There's G hat up there. And I'm going to take in each case, G hat comes with a natural embedding into GLNC. And so I recall that G's odd orthogonal, symplectic, even orthogonal, and then G hat is symplectic, odd orthogonal, and even orthogonal complex groups. And then capital N, then the one that receives the embedding of these L groups, that's going to be GL2NC in this case, GL2N plus 1C in this case, and GL2NC in this case. So I'm going to take the standard embedding rho of G hat into GLNC. So what the reference that I gave at the beginning does is to classify, and using trace formulas, the automorphic representations of these other classical groups in terms of the automorphic representations of general linear groups. The latter are the things that we understand pretty well with all of these extra things, and so the goal then has been to classify representations of these other families in terms of automorphic representations of general linear groups. All right, so here's the first theorem that I would say in that direction. Functoriality, principle of functoriality, so remember that applies to two different groups and a map of a homomorphism of the first dual group into the second dual group. And so the assertion is that functoriality holds, as I've defined in that very precise form, it holds for this rho, this natural embedding. In other words, the automorphic families C sub G for G map into the automorphic families C sub N for GLN. So that's the main import of this theorem. It's not hard to show these additional points. The mapping from GL, the resulting mapping from C of G to C of N is in fact injective, at least in the cases Bn and Cn, and also in the case Dn, if we make a minor adjustment, if we take conjugacy in G hat, that's this SO2N, C, by actually O2N. That's a slightly bigger group than the dual group, which we're really supposed to be taking conjugacy by. SO2N, this is a slightly bigger group. This is of index 2. So we take a conjugacy by O2N instead of SO2N, and then it's injective in that case. And the third assertion is, in fact, I don't want to contradict myself, I was claiming that you can't write down explicitly what the image C of N is, but with that proviso, there is a simple description of the image of C of G in terms of the elements in here as a subset of this. So that's the first theorem that says that the data, the automorphic data attached to these classical groups, that it is contained in the automorphic data attached to general linear groups. Okay, so this is step one of the classification of automorphic representations pi of G in terms of those of GLN. Now, here is a caution. The theorem of Jacquet-Schaleike or Muglin and Walsberger for GLN does not hold. It's been known for a long time, I guess, that it would fail spectacularly for these classical groups. The mapping of automorphic representations of one of these other classical groups into its corresponding family of semi-simple conjugacy classes in its dual group, unlike the case of GLN, is far from being injective. So that's already as a problem that has to be dealt with. So there's two more steps then. If the theorem I wrote down is step one, then there's two more steps that you would want to do for classical groups to classify their representations. One, understanding that the mapping from representations to families of conjugacy classes up there, understanding that it's not injective, well then classify its pre-image. Right, I'm going to write that. And this is supposed to be a capital pi. It's supposed to stand for a family of representations. Characterize its pre-image, pi sub c, a family of representations, automorphic representations of G. What's the pre-image of any one of these classes in C of G? This is what's known. These sets are what is known as L packets, or slightly more general packets than Langland's packets, specifically global packets. And they turn out to be products of local packets attached to that would be attached to the local constituents of pi. So in order to do this step, okay, you want to understand the pre-image of this. You are forced to deal with, so far we've gotten off very easily. We have dealt only with the unramified constituents of an automorphic representation, which have this beautiful and very simple classification. But if you're going to deal with the pre-image, again, that's a capital pi. It's a set of representations attached to a given family C. If you're going to deal with that, you better deal with all of the representations, the ramified ones as well. Okay, so you're going to have to deal with pi v when it's not unramified. In other words, you're going to have to come up with a classification of all irreducible representations of a real or p-adic group in the case of these classical groups. Classification of representations of, say, the symplectic group over the reals or the symplectic group over the p-adics, because that's going to have to be part of this packet. For real groups, this is known. At least much of it is known. It's due to Diana Shellstad building on the monumental results of Harishchandra. He studied representations of real groups and found with great power, he was an extremely powerful mathematician, and he ended up actually with a little addition by Langlands in the not so little, but with the complement by Langlands in the 1970s, ended up with a description of all of the representations of a real group, where V is the reals of GR, for any group, not just one of these classical groups. There's a list of them. And then what Shellstad did was to organize the elements, the representations in this list that comes from Harishchandra and Langlands, into packets, which are known as local L packets, or somewhat more general packets that are required for global applications. So for real groups, this problem is solved, but one needs to solve it for these classical groups, for p-adic groups as well. All right, that's step two. The pre-image, pi sub c, is going to be defined as a product over all V of packets, as I've alluded to, at each of the completions V of Q. All right, so now you have the pre-image there. Then there I've got a capital pi. This is the pre-image. For any little pi in capital pi, then the problem is, you're talking about automorphic representations. You want constituents of the spectrum. So it doesn't do just to say it occurs in it. You want an explicit description of how it occurs. And the discrete spectrum is the most important part. One can, again, by another sort of monumental contribution of Langlands, for any group, he showed how to construct the continuous spectrum of automorphic representations if you knew about the discrete spectrum for G and for smaller groups. So the main point is the discrete spectrum. And step 3, for any pi in this pre-image, find an explicit formula for its multiplicity in the discrete spectrum. So that's so that means you got to work with this set that you've constructed in step 2. I'm saying that in order to complete theorem 1, which was step 1, it's forced on you to find a classification, and this is known as putting them into packets like this is known as the theory of endoscopy. Again, another series of conjectures of Langland's. And so this would be an endoscopic classification of representations of these local groups. All right, so now I have about 10 minutes left, do I? Where's Alejandro? 5 minutes, okay, so I'm going to go very fast. This last part is more technical, I think. And I won't be able to finish the description of the solutions. So the bottom line is steps 2 and 3 have been completed. So we have a whole classification. And I should add that this comes from a sustained comparison of trace formulas. And it is still conditional on a trace formula exists for any group G over Q. Something further, a refinement known as the stabilization of the trace formula, has also been proved thanks to the because it's built on the proof of the fundamental lemma by Ngo. You need that. You need both of those. You also need what's known as the twisted trace formula, which is a generalization of it, and you need a stabilization of the twisted trace formula. Now, all of the fundamental lemmas that would be part of that have been proved, but there's still a lot of work that's basically adapting the techniques of the stabilization of the ordinary trace formula to the twisted case. That is still under construction. Muglin and Walsberger are attacking this problem in, I would say, a very sustained way. So, but without the stabilization of the twisted trace formula, these results are still conditional. So let me just say that this is the local part of the step 2, and what sort of very interesting, based on the theory of Langland's. They're based on a group introduced by Langland's, a pretty concrete group. It's the product of, it's equal to what's known as the Weil group. So now F is a local field. I guess we didn't put that in. F is a local field. So for example, F is the reals or the p-adics, or actually some algebraic extension of them. And then for any such F, there's a group, by definition, the Weil group, if F is Archimedean, or the Weil group cross SU2, if F is p-adic. And then we take phi of G to be the set of all homomorphisms of this locally compact group I haven't defined G sub L. If G is split, which is what we have been assuming, then GL is just the dual group, G hat. Taken up to G conjugacy. And then pi of G is the set of irreducible representations pi of G of F up to equivalence. All right, now there's various variants of these two things. So the idea is that representations of GR, this group, or GQV, this group of this local group, should be, roughly speaking, parameterized by these. These are known as Langland's parameters, and there should be a set, for any such Langland's parameter, there should be a finite set of representations known as an L packet, which are disjoint and whose union exhausts the set of all such representations. Okay. Well, there's variants of these sets, which I can, I don't know if this is being filmed, but there they are. And then we have the following theorem, There's objects you can associate to any parameter, namely essentially the centralizer of its image, an interesting little subgroup of G hat, and then its little finite group of connected components. That's a finite abelian 2 group in the classical case. And the assertion is that for any psi, there is a finite set. I'm calling it a multi-set because it's actually a set, a finite set over this set of unitary representations in G. It's set with multiplicities, finite set, together with a canonical mapping into the group of characters onto this little 2 group. It's defined in a very concrete way, namely by relations that characters and twisted characters satisfy. Characters are fundamental invariants of representations. And then we have the second part, which is the local Langlands classification for G. I'm sorry, I ran those other parameters by you rather quickly. These parameters, general parameter is psi. It's a generalization of the Langlands parameter that I introduced about 20 years ago. And suppose you, however, just take a Langlands parameter, which is the homomorphisms of the group LF, then the elements in this packet are tempered and multiplicity free. They're not multi-sets, they're just subsets. And the mapping from here to here is injective, that's a J, and bijective if F is p-adic. And moreover, the set of all tempered representations, they're the ones that come into the Plancherel formula for GQP, is a disjoint union of all of these. So a very sort of natural classification of the tempered representations of the group GQV. So that's the solution of the problem. That's the solution of step 2. Step 3 then is a very concrete multiplicity formula for any representation in the product of all of these local packets. These packets there. Take the product overall of a bunch of these things, and then it's a multiplicity formula, explicit multiplicity formula for any representation in that global packet in the discrete spectrum. All right, thank you very much.